Tellurium is a chemical element with symbol Ti and atomic number 52. It is a brittle, mildly toxic, rare, silver-white metalloid. Tellurium is chemically related to selenium and sulfur. It is occasionally found in native form, as elemental crystals. Tellurium is far more common in the universe as a whole than it is on Earth. Its extreme rarity in the Earth's crust, comparable to that of platinum, is partly due to its high atomic number, but also due to its formation of a volatile hydride which caused the element to be lost to space as a gas during the hot nebula formation of the planet. Tellurium was discovered in the Habsburg Empire in 1782 by Franz Joseph Müller von Reichenstein in a mineral containing tellurium and gold. Martin Heinrich Klaproth named the new element in 1798 after the Latin word for earth, tellus. Gold telluride minerals are the most notable natural gold compounds. However, they are not a commercially significant source of tellurium itself, which is normally extracted as a byproduct of copper and lead production. Commercially, the primary use of tellurium is in alloys, foremost in steel and copper to improve machinability. Applications in CDTE solar panels and as a semiconductor material also consume a considerable fraction of tellurium production. Tellurium has no biological function, although fungi can incorporate it in place of sulfur and selenium into amino acids such as tellurocysteine and tellurimethionine. In humans, tellurium is partly metabolized into dimethyl telluride, 2-Te, a gas with a garlic-like odor which is exhaled in the breath of victims of tellurium toxicity or exposure. Characteristics. Physical properties. Tellurium has two allotropes, crystalline and amorphous. When crystalline, tellurium is silvery white, and when it is in pure state it has a metallic luster. It is a brittle and easily pulverized metalloid. Amorphous tellurium is a black-brown powder prepared by precipitating it from a solution of tellurous acid or telluric acid 6. Tellurium is a semiconductor that shows a greater electrical conductivity in certain directions which depends on atomic alignment. The conductivity increases slightly when exposed to light. When in its molten state, tellurium is corrosive to copper, iron and stainless steel. Of the chalcogens, tellurium has the highest melting and boiling points, at 722.66 K and 1261 K, respectively. Chemical properties. Tellurium adopts a polymeric structure, consisting of zigzag chains of Te atoms. This gray material resists oxidation by air and is non-volatile. Isotopes. Naturally occurring tellurium has 8 isotopes. 5 of those isotopes, 122 Te, 123 Te, 124 Te, 125 Te and 126 Te, are stable. The other 3, 120 Te, 128 Te and 130 Te, have been observed to be radioactive. The stable isotopes make up only 33.2% of the naturally occurring tellurium. This is possibly due to the long half-lives of the unstable isotopes. They are in the range from 1013 to 2.2 times 1024 years. This makes 128 Te the isotope with the longest half-life among all radionuclides, which is approximately 160 trillion times the age of the known universe. There are 38 known nuclear isomers of tellurium with atomic masses that range from 105 to 142. Tellurium is among the lightest elements known to undergo alpha decay, with isotopes 106 Te to 110 Te being able to undergo this mode of decay. The atomic mass of tellurium exceeds that of the following element: iodine. Occurrence within abundance in the Earth's crust comparable to that of platinum. Tellurium is one of the rarest stable solid elements in the Earth's crust. Its abundance is about 1 microgram per kilogram. In comparison, even the rarest of the lanthanides have crustal abundances of 500 micrograms per kilogram. The extreme rarity of tellurium in the Earth's crust is not a reflection of its cosmic abundance, which is in fact greater than that of rubidium, even though rubidium is 10,000 times more abundant in the Earth's crust. The extraordinarily low abundance of tellurium on Earth is rather thought to be due to conditions in the Earth's formation, when the stable form of certain elements, in the absence of oxygen and water, was controlled by the reductive power of free hydrogen. Under this scenario, certain elements such as tellurium, which form volatile hydrides, were severely depleted during the formation of the Earth's crust. Through evaporation of these hydrides, tellurium and selenium are the heavy elements most depleted in the Earth's crust by this process. Tellurium is sometimes found in its native form, but is more often found as the tellurides of gold such as calaverite and krennerite, petsite, Ag3Out A2, and sylvanite, Ag4. The city of Telluride, Colorado was named in hope of a strike of gold telluride. Gold itself is usually found uncombined, but when found naturally as a chemical compound, it is most often combined with tellurium. Although tellurium is found with gold more often than in uncombined form, it is found even more often combined with elements other than gold, as tellurides of more common metals. Natural tellurite and tellurite minerals also occur, formed by oxidation of tellurides near the Earth's surface. In contrast to selenium, tellurium is not in general able to replace sulfur in its minerals, due to the large difference in ion radius of sulfur and tellurium. In consequence, many common sulfide minerals contain considerable amounts of selenium, but only traces of tellurium. In the gold rush of 1893, diggers in Kalgoorlie discarded a pyritic material which got in their way as they searched for pure gold. The Kalgoorlie waste was thus used to fill in potholes or as part of sidewalks. 3 years passed before it was realized that this waste was calaverite, a telluride of gold that had not been recognized. This led to a second gold rush in 1896, which included mining the streets. History. Tellurium was discovered in the 18th century in a gold ore from the mines in Zlatna, near today's city of Alba Iulia, Romania. This ore was known as Faxi-Biovices Blattridges Golders, or Antimonalischer gold keys, and, according to Anton von Ruprecht, was Spießglaskönig, containing native antimony. In 1782, Franz Joseph Müller von Reichenstein, who was then serving as the Austrian chief inspector of mines in Transylvania, concluded that the ore did not contain antimony, but that it was bismuth sulfide. The following year, he reported that this was erroneous and that the ore contained mostly gold and an unknown metal very similar to antimony. After a thorough investigation which lasted for 3 years and consisted of more than 50 tests, Müller determined the specific gravity of the mineral and noted the radish-like odor of the white smoke which passed off when the new metal was heated, the red color which the metal imparts to sulfuric acid, and the black precipitate which this solution gives when diluted with water. Nevertheless, he was not able to identify this metal and gave it the names aurum paradoxium and metallum problematicum, as it did not show the properties predicted for the expected antimony. In 1789, a Hungarian scientist, Pauk Hitibel, also discovered the element independently in an ore from Deutschpilsen which had been regarded as argentiferous molybdenite, but later, he gave the credit to Müller. In 1798, it was named by Martin Heinrich Klaproth, who had earlier isolated it from the mineral calaverite. The 1960s brought growth in thermoelectric applications for tellurium, as well as its use in free machining steel, which became the dominant use. Production. The principal source of tellurium is from anode sludges produced during the electrolytic refining of blister copper. It is a component of dusts from blast furnace refining of lead. Treatment of 1,000 tons of copper ore typically yields 1 kilogram of tellurium. Tellurium is produced mainly in the United States, Peru, Japan and Canada. For the year 2009, the British Geological Survey gives the following numbers. United States 50T, Peru 7T, Japan 40T and Canada 16T. The anode sludges contain the selenides and tellurides of the noble metals and compounds with the formula M2Te or M2Te. At temperatures of 500 degrees Celsius, the anode sludges are roasted with sodium carbonate under air. The metal ions are reduced to the metals, while the telluride is converted to sodium tellurite. M2Te plus O2 plus Na2CO3 Na2TO3 plus 2M plus CO2 tellurites can be leached from the mixture with water and are normally present as hydrotellurites HTO3- in solution. Selenites are also formed during this process, but they can be separated by adding sulfuric acid. The hydrotellurites are converted into the insoluble tellurium dioxide while the selenites stay in solution. HTO-3 plus O- plus H2SO4 TO2 plus SO2-4 plus 2H2O. The reduction to the metal is done either by electrolysis or by reacting the tellurium dioxide with sulfur dioxide in sulfuric acid. TO2 plus 2SO2 plus 2H2O Te plus 2SO2-4 plus 4H plus. Commercial grade tellurium is usually marketed as 200 mesh powder but is also available as slabs, ingots, sticks, or lumps. The year-end price for tellurium in 2000 was $14 per pound. In recent years, the tellurium price was driven up by increased demand and limited supply, reaching as high as $100 per pound in 2006. Despite an expected doubling in production due to improved extraction methods, the United States Department of Energy anticipates a supply shortfall of tellurium by 2025. Compounds. See also the categories tellurium compounds and telluride minerals. Tellurium belongs to the same chemical family as oxygen, sulfur, selenium and polonium, the chalcogen family. Tellurium and selenium compounds are similar. It exhibits the oxidation states -2, +2, +4 and +6, with the +4 state being most common. Telluride's reduction of Te metal produces the tellurides and polytellurides, 10⁻². The -2 oxidation state is exhibited in binary compounds with many metals, such as zinc telluride, ZnTe, formed by heating tellurium with zinc. Decomposition of ZnTe with hydrochloric acid yields hydrogen telluride, a highly unstable analog of the other chalcogen hydrides, H2O, H2S and H2She. ZnTe plus 2 hydrogen chloride ZnCl2 plus H2Te. H2Te is unstable, whereas salts of its conjugate base, TEH- are stable. Halides. The +2 oxidation state is exhibited by the diff halides, TeCl2, TeBr2 and TeI2. The dihalides have not been obtained in pure form, although they are known decomposition products of the tetrahalides in organic solvents, and the derived tetrahalotellurates are well characterized. Te plus X2 plus 2X minus Tex2 minus 4 where X is Cl, Br, or I. These anions are square planar in geometry. Polynuclear anionic species also exist, such as the dark brown Te2I2-6, and the black Te4I2-14. Fluorine forms 2 halides with tellurium. The mixed valence, Te2F4 and TeF6. In the +6 oxidation state, the OTeF5 structural group occurs in a number of compounds such as HOTIF5, B3XE2, Te4 and Te6. The square antiprismatic anion TeF2-8 is also attested. The other halogens do not form halides with tellurium in the +6 oxidation state, but only tetrahalides in the +4 state, and other lower halides. In the +4 oxidation state, halotellurate anions are known, such as TeCl2-6 and Te2Cl2-10. Halo-tellurium cations are also attested, including TeI+3, found in TeI3AsF6. Oxxo compounds tellurium monoxide was first reported in 1883 as a black amorphous solid formed by the heat decomposition of Tesa-3 in vacuum, disproportionating into tellurium dioxide, TiO2, and elemental tellurium upon heating. Since then, however, some doubt has been cast on its existence in the solid phase. Although it is known as a vapor phase fragment, the black solid may be merely an equimolar mixture of elemental tellurium and tellurium dioxide. Tellurium dioxide is formed by heating tellurium in air, causing it to burn with a blue flame. Tellurium trioxide, beta-TiO3, is obtained by thermal decomposition of Te6. The other two forms of trioxide reported in the literature, the alpha and gamma forms, were found not to be true oxides of tellurium in the +6 oxidation state, but a mixture of Te4+, O- and O-2. Tellurium also exhibits mixed valence oxides, Te2O5 and Te4O9. The tellurium oxides and hydrated oxides form a series of acids, including tellurous acid, orthotelluric acid 6, and metatelluric acid N. The two forms of telluric acid form tellurate salts containing the TiO2-4 and TiO6-6 anions, respectively. Tellurous acid forms tellurite salts containing the anion TiO2-3. Other tellurium cations include TeF2+8, which consists of two fused tellurium rings, and the polymeric TeF2+7. Zintyl cations. When tellurium is treated with concentrated sulfuric acid, it forms red solutions containing the zintyl ion, Te2+4. The oxidation of tellurium by AsF5 in liquid SO2 also produces this square planar cation, as well as with the trigonal prismatic yellow-orange Te4+6. 4Te+3 AsF5 Te2+4 2 AsF3 6 Te+6 AsF5 Te4+6 4+2 AsF3. Other tellurium zintyl cations include the polymeric Te2+7 and the blue-black Te2+8, which consists of two fused 5-membered tellurium rings. The latter cation is formed by the reaction of tellurium with tungsten hexachloride. 8Te+2 WCl6 Te2+8. 2 interchalcogen cations also exist, such as Te2She2+6 and Te2She2+8. These are formed by oxidizing mixtures of tellurium and selenium with a SF5 or SbF5. Organotellurium compounds. Tellurium does not readily form analogues of alcohols and thiols, with the functional group TEH, and are called tellurols. The TEH functional group is also attributed to using the prefix tellinol. Like H2Te, these species are unstable with respect to loss of hydrogen. Tellura others are more stable as are telluroxides. Applications. Metallurgy. The largest consumer of tellurium is metallurgy, where it is used in iron, copper and lead alloys. When added to stainless steel and copper, it makes these metals more machinable. It is alloyed into cast iron for promoting chill for spectroscopic purposes, as the presence of electrically conductive free graphite tends to deleteriously affect spark emission testing results. In lead, it improves strength and durability and decreases the corrosive action of sulfuric acid. Semiconductor and electronic industry uses tellurium as used in cadmium telluride solar panels. National Renewable Energy Laboratory lab tests using this material achieved some of the highest efficiencies for solar cell electric power generation. Massive commercial production of CDTE solar panels by First Solar in recent years has significantly increased tellurium demand. If some of the cadmium in CDTE is replaced by zinc, then Te is formed, which is used in solid-state X-ray detectors, alloyed with both cadmium and mercury, to form mercury-cadmium telluride. An infrared-sensitive semiconductor material is formed. Organotellurium compounds such as dimethyl telluride, diethyl telluride, diisopropyl telluride, diallyl telluride and methylallyl telluride are used as precursors for metal-organic vapor phase epitaxy growth of EV compound semiconductors. Diisopropyl telluride is employed as the preferred precursor for achieving the low-temperature growth of CDHGTE by MOVP. For these processes, highest purity metal organics of both selenium and tellurium are used. The compounds for semiconductor industry and are prepared by adduct purification. Tellurium as a tellurium suboxide is used in the media layer of several types of rewritable optical discs, including rewritable compact discs, rewritable digital video discs and rewritable Blu-ray discs. Tellurium dioxide is used to create acousto-optic modulators for confocal microscopy. Tellurium is used in the new phase-change memory chips developed by Intel. Bismuth telluride and lead telluride are working elements of thermoelectric devices. Lead telluride is used in far-infrared detectors. Other uses used to color ceramics. The strong increase in optical refraction upon the addition of selenides and tellurides into glass is used in the production of glass fibers for telecommunications. These chalcogenide glasses are widely used. Mixtures of selenium and tellurium are used with barium peroxide as oxidizer in the delay powder of electric blasting caps. Organic tellurides have been employed as initiators for living radical polymerization, and electron-rich mono and ditellurides possess antioxidant activity. Rubber can be vulcanized with tellurium instead of sulfur or selenium. The rubber produced in this way shows improved heat resistance. Tellurite agar is used to identify members of the Corynebacterium genus, most typically Corynebacterium diphtheria, the pathogen responsible for diphtheria. The tellurium is a key constituent of high-performing mixed oxide catalysts for the heterogeneous catalytic selective oxidation of propane to acrylic acid. The surface elemental composition changes dynamically and reversibly with the reaction conditions. In the presence of steam, the surface of the catalyst is enriched in tellurium and vanadium, which translates into the enhancement of the acrylic acid production. Biological role. Tellurium has no known biological function, although fungi can incorporate it in place of sulfur and selenium into amino acids such as tellurocysteine and telluromethionine. Organisms have shown a highly variable tolerance to tellurium compounds. Many cells, such as Pseudomonas aeruginosa, take up tellurite and reduce it to elemental tellurium, which accumulates and causes a characteristic and often dramatic darkening of cells. In yeast, this reduction is mediated by the sulfate assimilation pathway. Tellurium accumulation seems to account for a major part of the toxicity effects. Many organisms also metabolize tellurium partly to form dimethyl telluride, although dimethyl ditelluride is also formed by some species. Dimethyl telluride has been observed in hot springs at very low concentrations.